Hello everyone, today we'll study vector space. First of all, let me show you what is a vector space. Let V be a set of objects with two operations, vector addition and scalar multiplication. Let U, V, W be elements in set V, and let K and M be scalars. If all following 10 axioms are satisfied, then V is called a vector space, and all objects in V are called vectors. So let's take a look on these 10 axioms. First axiom says, for all UV in V, for all UV in set V, U plus V also belong to set V. The first axiom, if it's satisfied, is called closed under vector addition. If the first axiom is satisfied, it's called closed under vector addition. Second axiom says U plus V is the same as V plus V. U plus V is the same as V plus U. That's called commutativity. Third axiom says U plus V plus W is the same as U plus V, then plus W. That's called associativity. The fourth axiom says there exists a zero vector. There exists a zero vector denoted by 0 in V, such that 0 plus U is the same as U plus 0 equal to U for all U in V. 0 plus U equal to U plus 0 equal to U for all U in V. The fifth axiom says, for all U in V, there exists an additive inverse of U, denoted by negative U in V, such that U plus negative U is the same as negative U plus U equal to 0. Axiom 6 says, for all U in V, KU also belong to V. If axiom 6 is satisfied, we say set V is closed under scalar multiplication. If axiom 6 is satisfied, we say set V is closed under scalar multiplication. Axiom 7 says scalar K times U plus V is the same as KU plus KV. Axiom 8 says K plus M times U is the same as KU plus MU. Axiom 9 says K times MU is the same as Km times U. K times MU is the same as Km, scalar K times M first, and then times vector U. Axiom 10 says 1 times U equal to U. Axiom 10 says 1 times U equal to U. If in a set V with vector addition and scalar multiplication, if all 10 axioms are satisfied, we say V is a vector space. But if one of the axioms is failed, if one of the axioms is not satisfied, then we say V is not a vector space. If all 10 axioms are satisfied, then we say V is a vector space. But if one of the axioms is not satisfied, then V is not a vector space. Next, let's create an example. Show that R2 with the standard operations is a vector space. What does standard operation in R2 means? First of all, let U equal to U1, U2, V equal to V1, V2, W equal to W1, W2, be elements in R2. And let K and M be scalars. Standard operation, it means when we add vector U plus V, we add the corresponding components. Standard operation, it means when we add vectors U plus V, we add the corresponding entries. u1 plus v1, that's the first component. And u2 plus v2, that's the second component. And for scalar multiplication, k times u, we take k, multiply to both components in u. We get ku1 comma ku2. Those are called standard operations. Those are called standard operations in R2. Those are called standard operations in R2. Now, in order to show R2 is a vector space, we must verify all 10 axioms. Axiom 1, we must check R2 is closed under addition. So, u plus v, by definition, that's u1 plus v1, comma u2 plus v2. This vector has two components. This vector has two components of real numbers. So this vector belongs to R2. So it satisfies axiom 1. U plus v belongs to R2. It's closed under addition. R2 is closed under addition. Next, let's check commutativity. For axiom 2, try to verify u plus v is the same as v plus u. So we know that u plus v is u1 plus v1, comma u2 plus v2. V plus u is v1 plus u1, v2 plus u2. And we know that here, u1, v1, u2, v2, they are real numbers. For real numbers, we can switch orders. So u1 plus v1 is the same as v1 plus u1. u2 plus v2 is the same as v2 plus u2. That's the same as vector v plus u. That's the same as vector u plus v. So u plus v is the same as v plus u. It satisfies axiom 2. Axiom 3 is about associativity. We have to verify that u plus v plus w is the same as u plus w, u plus v first, then plus w. So let's first of all verify left side. Left hand side we have u plus v. We have u plus v plus w. Do the parentheses first. If we do the parentheses first, we get vector u is u1, comma u2. V plus w, we add the corresponding components. We get v1 plus w1, comma v2 plus w2. Then, when we add the vectors, we add the corresponding components. We get u1 plus v1 plus w1, comma u2 plus v2 plus w2. Since u, v, w, they are real numbers here, so we can switch order. Since they are real numbers, we can switch order. We can write it as u1 plus v1 plus w1, comma u2 plus v2 plus w2. That's the same as vector u1 plus v1, comma u2 plus v2 plus vector w1 plus w2. I can write this as the sum of two vectors. And then here, u1 plus v1, comma u2 plus v2, that's the same as vector u plus v. And the vector w1, comma w2, vector w1, comma w2, that's vector w. So it satisfies axiom 3. So here axiom 3 is satisfied. U plus v plus w is the same as u plus v plus w. So axiom 3 is satisfied. Next, let's try to verify axiom 4. There exists a zero vector such that 0 plus u equal to u plus 0 equal to u. So how can we find the zero vectors here? How can we find the zero vectors? So let's find the zero vector first. Zero vector, be very, very careful. In general, the zero vector in a vector space, zero vector is not always 0, 0. Zero vector is not always 0, 0. It could be 0, 0, but it's not always 0, 0. Be very, very careful. In your vector space, the zero vector is not always 0, 0. It could be 0, 0, but it's not always 0, 0. So here, let's find the zero vector first. First of all, let the zero vector 0 equal to S1, S2. We don't know what it is. Let's find S1, S2 first. Let's find the zero vector first. And we know that for zero vector, 0 plus u equal to u. We know that for zero vector, 0 plus u equal to u. And we know that when we add 0 to u, we add the corresponding entries. We add the corresponding components. We have S1 plus U1, S2 plus U2. So 0 plus U is S1 plus U1, S2 plus U2. On the right side, that equal to vector U. Vector U is U1, U2. Then, by matching the component, we can see that S1 plus U1 equal to U1, S2 plus U2 equal to U2. By matching the component, we can see that here, S1 plus U1 equal to U1, S2 plus U2 equal to U2. In the first equation, if I subtract U1 from both sides, I get S1 equal to 0. In the second equation, if I subtract U2 from both sides, I get S2 equal to 0. Which means the zero vector is 0, 0. That's a coincidence. Zero vector is not always 0, 0. In this case, zero vector is 0, 0, but it's not always 0, 0. And we know that 0 is a real number. This 0 is that's another real number. 0 vector is a pair of real numbers. So 0 belongs to R2. And we can verify that 0 plus u is the same as u plus 0 equal to u. And we can verify that 0 plus u equal to u. U plus 0 is also u. If I take vector u plus vector 0, it's also u. So there exists a zero vector in R2 such that 0 plus u equal to u plus 0 equal to u. So SCM4 is satisfied. Next, let's verify SCM5. SCM5 says, for each u in V, there exists an additive inverse of u, such that u plus negative u is the same as negative u plus u equal to 0. So let's try to find negative u. And again, be very, very careful. Negative u is not always the same as negative u1, negative u2. Negative u is not always negative u1, negative u2. It could be something else. It may be negative u1, negative u2, but it could be something else. It's not always in a vector space. Negative u is not always negative u1, negative u2. Be very, very careful. Negative u, it could be negative u1, negative u2, but not always negative u1, negative u2. Be very, very careful. So since we don't know what it is, negative u be y1, y2. We don't know what it is. Let negative u be y1, y2. We know that negative u plus u must be 0. Negative u plus u must be 0. So we take negative u plus vector u. Vector negative u is y1, y2. Vector u is u1, u2. If I add the vectors, we add their corresponding entries, add their corresponding components. We have y1 plus u1, y2 plus u2 equal to the 0 vector. And we know that 0 vector here is 0, 0. In this example, the 0 vector is 0, 0. Then, by matching the components, we can see that here. y1 plus u1 equal to 0. y2 plus u2 also equal to 0. In the first equation, if I subtract u1 from both sides, I get y1 equal to negative u1. In the second equation, if I subtract u2 from both sides, I get y2 equal to negative u2, which means negative u is negative u1 comma negative u2. Since u1, u2 they are real numbers, then negative u1, negative u2 they are also real numbers. So the vector negative u belongs to R2. So the vector negative u belongs to R2. And we know that negative u plus u is 0. U plus negative u, vector u plus negative u. If I add the corresponding entries, I also get 0. So axiom 5 is satisfied. Next, let's verify axiom 6. For axiom 6, what to verify? Ku belong to V. For axiom 6, try to verify for all vector u, for all scalar k, Ku belong to V. We know that Ku by the standard operation is Ku1 comma Ku2. Since u1, u2 they are real numbers, scalar k is also a real number. Real number times real number is real number. Real number times real number is real number. So Ku is a pair of real numbers. So Ku belongs to R2. That means R2 is closed under scalar multiplication. R2 is closed under scalar multiplication. It satisfies axiom 6. Next, let's verify axiom 7. Axiom 7 says k times u plus v equal to ku plus kv. So for k times u plus v, we do addition first. We do vector addition first. U plus v, by the standard operation, u plus v is u1 plus v1, comma u2 plus v2. K is a scalar. When we multiply a scalar to a vector, we multiply the scalar to both components in the vector. So I multiply k to both components. I get ku1 plus v1, comma ku2 plus v2. Then ku1 v1, ku2 v2, they are all real numbers. For real numbers, I can distribute. I get ku1 plus kv1, comma ku2 plus kv2. Then this vector can be rewritten as ku, comma ku1, comma ku2 plus kv1, comma kv2. If I pull out k, I get ku. If I pull out k here, I get kv. So let's satisfy axiom 7. Axiom 7 is satisfied. Next, let's verify axiom 8. Axiom 8 says k plus m times vector u is the same as vector k times vector u plus m times vector u. K plus m times u is the same as ku plus mu. So k plus m times u. Here I add a scalar first. K times m. K plus m stays the same. Vector u is u1, comma u2. When we multiply a scalar to a vector, we multiply the scalar to both components. I get k plus m times u1, comma k plus m times u2. kmu1, kmu2, they are all real numbers. For real numbers, I can distribute. I get ku1 plus mu1, comma, ku2 plus mu2. Then this vector can be rewritten as ku1, comma, ku2 plus mu1, comma, mu2. In the first vector, if I pull out k, I get ku1, comma, u2. In the second vector, if I pull out m, I get m, comma, u1, m of u1, comma, u2. That's k times vector u plus m times vector u. So SCN A is satisfied. K plus m times u equal to ku plus mu. That's SCN A. Next, let's verify SCN 9. K times mu equal to km times u. Here, km, they are scalars. For SCN 9, k times mu. So do the parentheses first. Take m times vector u first. When we have m times vector u, we take m, multiply to each component in vector u. I get mu1, comma, mu2. Next, we multiply k to this vector. When we multiply a scalar to a vector, we multiply the scalar to both components. We get k times mu1, comma, k times mu2. Since kmu1, kmu2, they are all real numbers. For real numbers, I can switch order like this. Km times u1, comma, km times u2. Then km is a scalar, I can put it outside. Km is a scalar, I can put it outside. If I pull out km, what's left is u1, comma, u2. And we know that u1, comma, u2 is vector u. So SCN 9 is satisfied. K times mu is the same as km times u. Next, let's verify SCN 10. SCN 10 says 1 times u equal to u. Let's verify SCN 10. 1 times u equal to u. Let's verify SCN 10. 1 times u. Here, consider 1 as a scalar. When we multiply a scalar to a vector, we multiply the scalar to both components in the vector. I get 1u1, comma, 1u2. We multiply the scalar to both components in the vector. And we know that 1u1 is the same as u1. 1u2 is the same as u2. They're equal to u. So 1u equal to u. SCN 10 is satisfied. If all 10 SCNs are satisfied, then we say R2 is a vector space. So R2 under the standard operation is a vector space. So if all 10 SCNs are satisfied, then a set is a vector space. But if one of the SCN is not satisfied, then the set is not a vector space. Next, let me show you a different example. Show that R2 under the following operations is not a vector space. Here we define a new operation in R2. For all u and v in R2, and for all scalar k, we define vector addition u plus v as u1 plus v1 plus 2, comma, u2 plus v2 plus 3. We define vector addition like this. u1 plus v1 plus 2, that's the first component, comma, u2 plus v2 plus 3, that's the second component, and we define scalar multiplication as ku equal to ku1, comma 0. We only multiply k to the first component. We set the second component to be 0. Under this operation, try to show that R2 is not a vector space. So let's verify the 10 axioms. First of all, let U be U1, U2, V be V1, V2, and W be W1, W2. Let U, V, W be vectors in R2. And let K and M be scalars. First axiom, we try to show that R2 is closed under addition. Vector U plus V. By definition here, we get U1 plus V1 plus 2, U2 plus V2 plus 3. Since U1, V1, number 2, U2, V2, number 3, they are all real numbers. So together we have a pair of real numbers. So U plus V belongs to R2. So axiom 1 is satisfied. R2 is closed under addition. Axiom 1 is satisfied. Next, let's verify axiom 2. For axiom 2, we try to verify U plus V equal to V plus U. Here, U plus V, we have U1 plus V1 plus 2, U2 plus V2 plus 3. How about V plus U? V plus U is V1 plus U1 plus 2, V2 plus U2 plus 3. Here you can see that they are the same. U plus V equal to V plus U. So axiom 2 is satisfied. Axiom 2 is satisfied. How about axiom 3? For axiom 3, we try to verify that U plus V plus W is the same as U plus V plus W. So U plus V plus W, we add the parentheses first. Vector U is U1, comma U2. Vector V plus W, that's V1 plus W1 plus 2. We are using the new definition here. We have V1 plus W1 plus 2, comma V2 plus W2 plus 3. That's V plus W. Next, add these two vectors. Add these two vectors. We have U1 plus the first component. When we add two vectors, we add the first components together, then add 2. Use this definition. We add these two vectors using this definition. This definition says we add the first component together, then plus 2. I get U1 plus V1 plus W1 plus 2 plus 2. That's the first component. I add the first component and then add 2. Then I add the second component, then add 3. So I get U2 plus V2 plus W2 plus 3 plus 3. If I simplify, I get U1 plus V1 plus W1 plus 4, comma U2 plus V2 plus W2 plus 6. That's U plus V plus W. Next, let's try to verify U plus V plus W. Are they the same? U plus V plus W. Do the parentheses first. For U plus V, use the new rule here. I get u1 plus v1 plus 2, comma, u2 plus v2 plus 3, plus w. W is a vector, w1, comma, w2. Then add the vectors. Apply the new rules. When adding these two rules says when adding two vectors, add the first component together, then add 2. Add the second component together, and then add 3. So I have u1 plus v1 plus 2 plus w1 plus 2. Add the first component together, then add 2. Then add the second component together and add 3. Then those are real numbers. We can simplify. We get u1 plus v1 plus w1 plus 4, comma, u2 plus v2 plus w2 plus 6. We can see that here, they're exactly the same. They're exactly the same. So axiom 3 is satisfied. U plus v plus w is the same as u plus v plus w. So axiom 3 is satisfied. Next, let's verify axiom 4. Next, let's verify axiom 4. Axiom 4 says there exists a zero vector. There exists a zero vector in V such that 0 plus u is the same as u plus 0 equal to u. Keep in mind, in a vector space, zero vector is not always 0, 0. Keep in mind, in a vector space, zero vector is not always 0, 0. So we need to find it. We don't know what it is. We need to find it here. We don't know what it is. So let the zero vector equal to s1, comma s2. We don't know what it is. So let the zero vector be s1, comma s2. Then for zero vector, we know that 0 plus u must equal to u. For zero vector, 0 plus u must equal to u. Here, zero vector is s1, comma s2. Vector u is u1, comma u2. When we add them, they equal to vector u, which is u1, comma u2. When we add two vectors, apply the new rule here. Here we define a vector addition in a new way. We add the first component at 2. Add the second component at 3. So when we add two vectors, s1, I get s1 plus u1 plus 2, comma s2 plus u2 plus 3. They equal to u1, comma u2. Then, by matching the first and the second component, we know that s1 plus u1 plus 2 equal to u1. s2 plus u2 plus 3 equal to u2. In the first equation, if I subtract u1 from both sides, I get s1 plus 2 equal to 0, which means s1 equal to negative 2. In the second equation, if I subtract u2 from both sides, I get s2 plus 3 equal to 0, which means s2 equal to negative 3. So the zero vector is negative 2, comma negative 3. s1, comma s2. Zero vector is s1, comma s2, which is negative 2, comma negative 3. That's the zero vector. And we know that negative 2, negative 3, they are real numbers. So zero vector belong to R2. Since there exists a 0 in R2, axiom 4 is satisfied. So axiom 4 is satisfied. Next, let's verify axiom 5. Let's verify axiom 5. Axiom 5 says, for each u in V, there exists an additive inverse of u, such that u plus negative u is the same as negative u plus u equal to 0. Keep it in mind. Be very, very careful. In a vector space, negative u is not always negative u1, negative u2. In a vector space, negative u is not always negative u1, negative u2. It could be negative u1, negative u2, but not always negative u1, negative u2. Be very, very careful. In a vector space, negative u is not always negative u1, negative u2. It could be, but not always. Since we don't know what it is, let negative u equal to y1, y2. Since we don't know what it is, let negative u equal to y1, comma y2. Then we know that negative u plus u must be 0. Negative u plus u must be 0. Negative u is the vector y1, comma y2. U is the vector u1, comma u2. And 0, the 0 vector here is negative 2, comma negative 3 we just found. The 0 vector is negative 2, comma negative 3. Now let's add the vectors using the new rule here. Let's add the vectors using the new rule. The new addition rule says, when we add two vectors, I add the first component, add 2. I add the second component, add 3. So apply the new rule. I add the first component, add 2. I get y1 plus u1 plus 2. And the second component, I get y2 plus u2 plus 3. That equal to negative 2, comma negative 3. Then, by matching the components, you can see that here, y1 plus u1 plus 2 equal to negative 2. y2 plus u2 plus 3 equal to negative 3. Then, in both equations, try to get y1, y2 by itself. In both equations, try to get y1, y2 by itself. In the first equation, if I ask for the y1 is negative u1 minus 4. y2 is negative u2 minus 6. So here we know that negative u is the vector negative u1 minus 4, comma negative u2 minus 6. For the vector negative u, the additive inverse negative u is negative u1 minus 4, comma negative u2 minus 6. Since u1, u2 they are real numbers, and 4 and 6 they are also real numbers, so negative u is a pair of real numbers. Negative u belong to R2. Since there exists negative u in R2, then axiom 5 is satisfied. Since there exists additive inverse for each u, axiom 5 is satisfied. Next, let's try to verify axiom 6. Axiom 6 says, for all vector u, for all scalar k, ku belong to V, which will show that V is closed under scalar multiplication. Here we try to show that R2 is closed under scalar multiplication. What's Ku here? By our new definition for scalar multiplication, Ku we take K multiplied to the first component and set the second component to be 0. When we take K times vector u, I take K multiplied to the first component and then set the second component equal to 0. So here, Ku is Ku1, comma 0. Since Ku1, 0, they are all real numbers. This is a pair of real numbers that belong to R2. So R2 is closed under scalar multiplication. Axiom 6 is satisfied. So axiom 6 is satisfied. Next, let's verify axiom 7. Is axiom 7 satisfied? Axiom 7 says k times u plus v equal to ku plus kv. Let's check axiom 7. K times u plus v. Let's do addition first. K times u plus v. For vector u plus v, let's apply the new definition. The new addition rule here is u1 plus v1 plus 2, comma, u2 plus v2 plus 3. u1 plus v1 plus 2, comma, u2 plus v2 plus 3. Then I take vector k, take scalar k, multiply to this vector. Next, take scalar k, multiply to this vector. So by the new multiplication rule here, when we multiply scalar to a vector, I take scalar, multiply to the first component, and set the second component to be 0. I multiply k to the first component. I get u1 plus v1 plus 2. I set the second component to be 0. That's k times u plus v. I multiply k to the first component and set the second component to be 0. Take k, multiply to the first component, and set the second component to be 0. Then when we multiply, we get ku1 plus kv1 plus 2k, comma 0. Now let's compute on the right side. ku plus kv. Then the right side we have ku plus kv. What's ku plus kv? Here we do multiplication first. We do scalar multiplication first. K times u. We multiply k to the first component and set the second component to be 0. For kv, we multiply k to the first component and set the second component to be 0. When we add the vectors, apply the new addition rule. When we add vectors, apply the new addition rule. We add the first component to the first component plus 2. I get ku1 plus kv1 plus 2. I add the second component to the second component and then add 3. I get 0 plus 0 plus 3, which is ku1 plus kv1 plus 2, comma 3. Here we can see that k times u plus v, we get this. Ku plus kv, we get this. They are not the same. So from here we can see that. K times u plus v is not the same as ku plus kv. Here, k times u plus v is not the same as ku plus kv. So axiom 7 is not satisfied. Axiom 7 is not satisfied. So axiom 7 is not satisfied. In general, if one of the axiom is not satisfied, that's enough to show that R2 under these two operations is enough to show that R2 under these two operations is not a vector space. If one of the axiom is not satisfied, that's enough to show that R2 under these two operations is not a vector space. But here, I'll keep going and find all axioms which are not satisfied. Axiom A, it says k plus m times u must be the same as ku plus mu. Let's do the left side first. k plus m times u. That's a scalar. K plus m is a scalar. U is a vector. When we have a scalar times a vector, we take the scalar times the first component. And the second component becomes 0. When we have a scalar times a vector, we take the scalar times the first component and set the second component to be 0. If I simplify, I get ku1 plus mu1, comma 0. That's k plus m times u. On the right side, what's ku plus mu? For ku plus mu, we multiply the scalar first. K times u, we take k, multiply to the first component. I get ku1. And I set the second component to be 0. For mu, I take m, multiply to the first component of vector u. I get mu1. And I set the second component to be 0. Next, add these vectors using the new rule. Add these vectors using the new rule. The new addition rule says, I add the first components, then plus 2. ku1 plus mu1 plus 2. Add the second components, then add 3. 0 plus 0 plus 3. That's the new addition rule. Add the first components, then add 2. Add the second components, then add 3. If I simplify, I get ku1 plus mu1 plus 2, comma 3. Here we can see that k plus m times u is not the same as ku plus mu. So here we can see that k plus m times u is not the same as ku plus mu. So axiom A is not satisfied. Axiom A is not satisfied. Next, let's verify axiom 9. Axiom 9 says k times mu must be the same as km times vector u. So on the left side, to show that k times mu. What's k times mu? Let's do the parentheses first. When we have m times u, we multiply m, multiply to the first component, and then set the second component to be 0. That's a new definition for scalar multiplication. Next, take k, multiply to this vector. Take k, multiply to this vector. By the new multiplication rule, I multiply k to the first component, and then set the second component to be 0. I get k times mu1, comma 0. Since k and mu1 they are all real numbers, it can be written as k mu1, comma 0. Next, let's compute on the right side. Km times u. What's km times u? Here we treat km as one scalar. When we have a scalar times a vector, we take the scalar, multiply to the first component, and set the second component to be 0. And then here we can see that kmu1, they are all real numbers. It can be rewritten as kmu1, comma 0. Here we can see that kmu1 is the same as km times u. K times mu is the same as km times u. So they are exactly the same. So axiom 9 is satisfied. So axiom 9 is satisfied. Next, let's verify axiom 10. Axiom 10 says 1 times u must be the same as u. Let's verify. What's 1 times u? 1 times u, we treat 1 as a scalar. For 1 times u, we treat 1 as a scalar. For scalar multiplication, the new rule says we multiply the scalar to the first component and set the second component to be 0. Since 1 is a scalar, I multiply 1 to the first component. I get 1u1 and set the second component to be 0, which is u1, 0. In general, u1, 0 is not the same as vector u. u1, 0 is not the same as vector u. Vector u is u1, u2. Vector u is u1, u2, so they are not the same, which means axiom 10 is not satisfied. So axiom 10 is not satisfied. Since axioms 7, 8, and 10 are not satisfied, R2 under these two operations is not a vector space. Since there are 3 axioms, these 3 axioms are not satisfied, R2 is not a vector space under these two operations. In general, if we find one axiom that's not satisfied, it's enough. In general, if we find one axiom which is not satisfied, that's enough to show the vector space. The set is not a vector space. Next example, let V be the set of all positive real numbers for all u and v in V, and for all scalar k, we define vector addition and scalar multiplication as the following. We define u plus v as u times v. We define vector addition u plus v as u times v. And we define scalar multiplication k times u as u to the power of k. Show that V is a vector space. So let's verify all 10 axioms. If all 10 axioms are satisfied, then V is a vector space. So first of all, let U, V, W be elements in set V. And let K and M be scalars. First axiom, we try to show that U plus V belongs to V. U plus V, by definition, U plus V, vector U plus V is U times V. And we know that U and V are positive real numbers. Positive real number times positive real number is positive. Positive number times positive number is positive. So U times V belong to R positive, belong to positive real numbers. So it satisfies axiom 1. Axiom 2, we know that U plus V equal to U times V, which is the same as V times U. For real numbers, U times V is the same as V times U. And V times U is the same as V plus U. That's the definition of vector addition. V plus U is V times U. So U plus V equal to U plus V equal to V plus U. It satisfies axiom 2. Axiom 3, U plus V plus W. For u plus v plus w, we do the parentheses first. We have u plus vw. For vector addition, v plus w, we write it as v times w. Then we have two vectors, u and vw. When we are adding two vectors, by definition of addition, when adding two vectors, we multiply these two numbers. We get u times vw. And on the other side, u plus v plus w. We do the parentheses first. Do u plus v first. U plus v is u times v. By definition of vector addition, that's u times v plus w. Then when we add two vectors, we write it as uv times w. Since uv, w, they are real numbers, when we multiply, both of them is the same as uv, w. So u plus v plus w is the same as u plus v plus w. So axiom 3 is satisfied. Axiom 4. What's the zero vector? What's the zero vector? Here, to avoid confusion, I write zero vector as a 0 with an arrow on top. To avoid confusion, I write 0 with an arrow on top. This represents zero vector. We don't know what's the zero vector, so let the zero vector be x. We don't know what's the zero vector, so let the zero vector be x. Zero vector is not necessarily 0, it could be something else. Zero vector is not necessarily 0, it could be something else. So let zero vector be x. We don't know what it is, but we know that zero vector plus u is always the same as u. Zero vector plus u is the same as u. And we know that zero vector is x. X plus u is the same as u. For vector addition, x plus u, that's the same as x times u. Since u is not 0, u is a positive real number, u is not 0, I can divide both sides by u. So s equal to 1, which means the zero vector is 1. Since 1 is a positive real number, 0 belongs to the vector space. So axiom 4 is satisfied. Since 1 is a positive real number, 0 belongs to the set. 0 belongs to the set. Zero vector belongs to the set. So axiom 4 is satisfied. Next axiom, we try to show that for all vector u, negative u exists, and additive inverse exists. But we don't know what it is. Let negative u be y. Then we know that negative u plus u is always a zero vector. Negative u is y, so y plus u is the zero vector. Zero vector is 1. Zero vector is number 1. Here, for y plus u, for vector addition y plus u, by the definition of vector addition, I multiply the numbers. I get y times u equal to 1. If I solve an equation for y, I can divide both sides by u. Since u is not 0, I can divide both sides by u. Y equal to 1 over u. So negative u is always 1 over u. Negative u is always 1 over u. And 1 divided by a non-zero real number. U is a positive real number. 1 divided by a positive real number is a positive real number. So negative u belongs to the set V. 1 divided by a positive real number is a positive real number. So negative u belongs to the set V. Axiom 6, we try to show that for all vector u, k times u belong to the vector space, belong to the set V. For scalar multiplication, k times u, by the definition of scalar multiplication, k times u is u to the power of k. U is a positive real number. Positive real number raised to any power is positive. Positive real number raised to any power is positive. So that belongs to between the set V. So V is closed under scalar multiplication. V is closed under scalar multiplication. It satisfies axiom 6. For axiom 7, we try to show that K times U plus V equal to KU plus KV. Let's do the left side first. Left side do the parentheses first. On the left side do the parentheses first. For vector addition, U plus V. U plus V, by the definition of vector addition, that's U times V. Now, U times V is a vector. K is a scalar. Scalar times a vector. Scalar times a vector. By the definition of scalar multiplication, we take a vector raised to the power of K. That's U to the power of K times V to the power of K. And we know that U to the power of K, that's KU. U to the power of K, that's K times U. V to the power of K, that's scalar K times vector V. That's a vector. That's a vector. When we multiply two vectors, that's the same as KU plus KV. KU times KV, that's the same as KU plus KV by the definition of vector addition. So axiom 7 is satisfied. Axiom 8. K plus M times U. We try to show that K plus M times U is the same as KU plus MU. Here, K plus M is a scalar. K plus M is a scalar. For scalar multiplication, we take a vector raised to the power of scalar. That's U to the power of K plus M. Then U to the power of K plus M can be rewritten as U to the power of K times U to the power of M. And we know that U to the power of K is KU. U to the power of M is MU. And for KU times MU, it can be rewritten as vector KU plus vector MU. So axiom 8 is satisfied. Axiom 9, we shall show that K times MU is the same as Km times U. So K times MU, do the parentheses first. In the parentheses, we have a scalar times a vector. When we have a scalar times a vector, take a vector raised to the power of the scalar. So in the parentheses, we get U to the power of M. Then we treat U to the power of M as a scalar, as a vector. K is a scalar, that's a vector. When we have a scalar times a vector, take the vector raised to the power of the scalar. This can be rewritten as U to the power of MK. Now here, if I treat MK as a scalar, if I treat MK as one scalar, U to the power of MK can be rewritten as MK times U. So axiom 9 is satisfied. Next, axiom 10. We have to show that 1 times vector U is U. Here 1 is a scalar, U is a vector. 1 times vector U can be noted as, for K times U, that's U to the power of K. So for 1 times vector U, that's U to the power of 1. And we know that U to the power of 1 is U. So 1U equal to U. Axiom 10 is satisfied. Since all 10 axioms are satisfied, then V is a vector space under these two operations. So R plus, a set of all positive numbers, is a vector space. Under these two operations. Next example, let V be a set of only one element, E. For all scalar K, let vector addition and scalar multiplication be defined as E plus E, vector E plus E equal to E, and scalar K times vector E equal to E. Show that V is a vector space. In order to show V is a vector space, we must show that the set V with these two operations satisfy all 10 axioms. So let's prove it. First of all, let vector U, V, W belong to V. Since set V has only one element, then we know that U is E, V is E, W is also E. If U, V, W belong to the set V, and there's only one element in V, then U must be E, V must be E, and W must be E. Let K and M be scalars. Axiom 1, we try to show that U plus V belong to the set V. What's U plus V? Since U is E, V is E, we have E plus E. And we know that by the definition of vector addition, E plus E equal to E. E belong to V. That means V is closed under vector addition. The set V is closed under vector addition. Next property, we try to show that U plus V equal to V plus U. That's called commutativity. We try to show that U plus V equal to V plus U. U plus V equal to E plus E. Since U and V, they are both E's. E plus E is E. V plus U is also E plus E. That's also E. So U plus V equal to V plus U. So axiom 2 is satisfied. Axiom 2 is satisfied since they both equal to E. Axiom 2 is satisfied. Axiom 3, let's call associativity. U plus V plus W. We try to show that they're equal to U plus V plus W. Here, U, V, W, they are all E's. So they're equal to E plus E plus E. Here, do the parentheses first. Inside the parentheses, E plus E is E. And then E plus E is E. That's the left side. On the right side, we have U plus V plus W. And we know that U, V, W, they are all E's. We have E plus E plus E. If you do the parentheses first, in the parentheses, E plus E is E. Then we know that E plus E is E. So U plus V plus W equal to U plus V plus W. So axiom 3 is satisfied. Axiom 3 is satisfied. Axiom 4, show that there exists a zero vector. Show that there exists a zero vector. Since there's only one element in the set V, the only possibility is that we let zero vector be E. Since there's only one E in the set, there's only one element in the set, the only possibility is that we let 0 be E. Then we know that 0 vector plus U, 0 vector plus U, that's E plus E. 0 is E, U is also E. They're equal to E. E is the same as U. So 0 vector plus U equal to U. U plus 0 is also E plus E equal to E equal to U. So axiom 4 is satisfied. Axiom 4 is satisfied. Axiom 5, we try to show that for all vector U, there exists an additive inverse. For all vector U, there exists an additive inverse. Here, the only possibility for the inverse is E. So let negative U equal to E. Then negative U plus U is E plus E. E plus E is E. And here, I try to show that negative U plus U is the zero vector. E is the zero vector. And similarly, U plus negative U is also E plus E. That's also the zero vector. So axiom 5 is satisfied. Next, axiom 6. KU. We try to show that KU belongs to V. We know that vector U is E. So we get K times E. Here we know that by definition of scalar multiplication, K times E is E. By the definition of a scalar multiplication, K times E is E. And we know that E belongs to V. So V is closed under scalar multiplication. Set V is closed under scalar multiplication. Axiom 7. We try to show that K times U plus V equal to KU plus KV. Let's do the left side first. For K times U plus V, since both U and V they are E's, we can plug in E for both U and V. Then do the parentheses first. In the parentheses, E plus E is E. We get KE, and we know that by definition of scalar multiplication, K times E is E. So here, K times U plus U, K times U plus V is E. From the right side, we have KU plus KV. Are they the same? Since U and V, they are both E's, I can write it as KE plus KE. Then, by the definition of the scalar multiplication, K times E is E. The other K times E is also E. E plus E equal to E. So, left side equal to the right side, they both equal to E. So, left side equal to the right side. K times U plus V equal to KU plus KV. That means axiom 7 is satisfied. Axiom 8. We have to show that K plus M times U equal to KU plus MU. Let's do the left side first. K plus M times U. We know that U is E. So plug in E for U. We get K plus M times E. K plus M is a scalar. K plus M is a scalar. By the definition of scalar multiplication, any scalar times E is E. Any scalar times E is E. That's a scalar. K plus M is a scalar. Any scalar times E is E. So the left side equal to E. On the right side of the equation, we have KU plus MU. We know that U is E, so I plug in E for U. I get KE plus ME. By the definition of scalar multiplication, any scalar times E is E. Any scalar times E is E. And by the definition of vector addition, E plus E is E. So left side equal to the right side. So K plus M times U equal to KU plus MU. Which means axiom 8 is satisfied. Axiom 9 says K times MU is the same as Km times U. Do the parentheses first. First of all, vector U is E. Vector U is E. Here M is a scalar. By definition of scalar multiplication, any scalar times E is E. So I get KE. Again, by the definition of scalar multiplication, any scalar times E is E. So left side, KMU equal to E. Now, from the right side, how about Km times U? We know that Km is a scalar. U is E. Vector U is E. By the definition of scalar multiplication, any scalar times E is E. This is one scalar. Km is one scalar. Any scalar times E is E. So left side equal to the right side. So K times MU equal to Km times U. So axiom 9 is satisfied. How about axiom 10? We try to show that 1U equal to U. Since U is E, 1U is the same as 1 times E. 1 is a scalar. By definition of scalar multiplication, any scalar times E equal to E. By the definition of scalar multiplication, any scalar times E equal to E. So 1 times E equal to E. E is the same as U. So we have 1U equal to U. Axiom 10 is satisfied. Since all 10 axioms are satisfied, that means vector V with these two operations is a vector space. So V is a vector space. Under these two operations. Next example, M22 is the set of all 2 by 2 matrices. Show that M22 is a vector space under the standard matrix operation. The standard matrix operation means when we add 2 matrices of the same size, we add the corresponding entries. When we multiply a scalar to a matrix, we multiply the scalar to every entries in the matrix. Let's prove it here. The UVW, the U equal to U11, U12, U21, U22. The V equal to V11, V12, V21, V22. The W equal to W11, W12, W21, W22 belong to M22. And let K and M be scalars. Let's verify all 10 axioms. If all 10 axioms are satisfied, that means M22 under these two operations is a vector space. First axiom, U plus V. We try to show that U plus V belong to M22. We try to show that M22 is closed under vector addition. So U plus V is U11, U12, U21, U22 plus vector V. Vector V is V11, V12, V21, V22. When we add 2 matrices under the standard operation, we add the corresponding entries. I get U11 plus V11, U12 plus V12, U21 plus V21, U22 plus V22. That's also a 2 by 2 matrix. So this matrix belongs to M22. This matrix belongs to M22. That means M22 is closed under addition, under vector addition. So axiom 1 is satisfied. Axiom 2, we try to show commutativity. That means we try to show U plus V equal to V plus U. For vector U plus V, we add the corresponding entries. I get U11 plus V11, U12 plus V12, U21 plus V21, U22 plus V22. Those U's and V's are real numbers. For real numbers, we can switch orders. So it can be rewritten as V11 plus U11, V12 plus U12, V21 plus U21, V22 plus U22. That's the same as V plus U. So axiom 2 is satisfied. U plus V equal to V plus U. That means axiom 2 is satisfied. axiom 3, we try to show associativity. Let me try to show that u plus v plus w is the same as u plus v plus w. So here, do the premises first. I first of all leave u the same. Okay, u11, u12, u21, u22. Leave vector u the same. Do the premises first. In the premises, vector v plus vector w. When we add the two vectors, by standard operation, we add the corresponding entries. I get v11 plus w11, v12 plus w12, v21 plus w21, v22 plus w22. Then, when we add these two matrices, we add the corresponding entries. They equal to u11 plus v11 plus w11. That's the first entry. Second entry, we get u12 plus v12 plus w12. Third entry, I get u21 plus v21 plus w21. For the fourth entry, we get u22 plus v22 plus w22. Those u's, v's, and w's, they are all real numbers. For real numbers, we can switch orders. It can be written as u11 plus v11 plus w11, since those are real numbers. u12 plus v12 plus w12. The third entry is u21 plus v21 plus w21. And the fourth entry is u22 plus v22 plus w22. Then, this can be rewrite as, I can separate uv and w. I can write it as two matrices, u11 plus v11, u12 plus v12, u21 plus v21, u22 plus v22. Then write w in another matrix. I get w11, w12, w21, w22. This is vector u plus v. This is vector w. So u plus v plus w is the same as u plus v first, then plus w. So axiom 3 satisfied. Axiom 3 is satisfied. Axiom 4, we try to show that there's a zero. There's a zero vector. Zero vector is not always 0, 0, 0, 0. It could be 0, 0, 0, 0, but it's not always 0, 0, 0, 0. Be very, very careful. Zero vector, it could be all zeros, but it's not always all zeros. Could be something else. Since we don't know what zero is, then the zero vector be x11, s12, x21, x22. We don't know what it is. Then the zero vector be x11, s12, x21, and s22. We don't know what it is. Then we know that since zero, that's a zero vector, we know that 0 plus u is always the same as u. For 0 plus u, this is zero vector, this is u. When we add two matrices of the same size, by standard operation, we add the corresponding entries. So 0 plus u is s11 plus u11, s12 plus u12, s21 plus u21, x22 plus u22 equal to u. U is this, u11, u12, u21, u22. Then, by matching the corresponding entries, we have s11 plus u11 equal to u11, x12 plus u12 equal to u12, x21 plus u21 equal to u21, x22 plus u22 equal to u22. In the first equation, if I subtract U11 from both sides, I get S11 equal to 0. In the second equation, if I subtract U12 on both sides, I get S12 equal to 0. In the third equation, if I subtract U21 on both sides, I get S21 equal to 0. In the fourth equation, if I subtract U22 on both sides, I get S22 equal to 0. Which means the 0 vector is 0, 0, 0, 0, but not always. In this case, it's 0, 0, 0, but 0 vector is not always 0, 0, 0, 0. So this is a 2 by 2 matrix. So the 0 vector belongs to M22. That means axiom 4 is satisfied. Next, axiom 5. We try to show that for each u, there exists an additive inverse, negative u. For each u, there exists an additive inverse, negative u. Negative u is not always negative u11, negative u12, negative u21, negative u22. Negative u is not always this vector, this matrix. It could be something else. It may be this matrix, but it could also be something else. We don't know what it is. Negative u may be this matrix, but it may be something else. We don't know what it is. Since we don't know what negative u is, negative u equal to y11, y12, y21, y22. Then we know that negative u plus u must be 0. For negative u plus u, when we add in two matrices of the same size, we add the corresponding entries. So I get y11 plus u11, y12 plus u12, y21 plus u21, y22 plus u22. The 0 vector is 0, 0, 0, 0. Then, by matching the entries, we know that y11 plus u11 equal to 0. y12 plus u12 equal to 0. y21 plus u21 equal to 0. And y22 plus u22 equal to 0. Then solve each equation for the y's. In the first equation, y11 is negative u11. In the second equation, y12 is negative u12. In the third equation, y21 is negative u21. In the fourth equation, y22 is negative u22, which means negative u is the matrix. Negative u11, negative u12, negative u21, and negative u22. This is a 2 by 2 matrix, so that belongs to M22. Since negative u belongs to M22, then axiom 5 is satisfied. Since for each u, negative u also belongs to M22, axiom 5 is satisfied. Axiom 6. We try to show that Ku also belongs to M22. We try to show that M22 is closed under scalar multiplication. Ku is the same as K times U. U is U11, U12, U21, U22. Under the standard matrix operation, scalar K, when we have a scalar K times a matrix, we multiply K to every entries. So I get Ku11, Ku12, Ku21, Ku22. This is a 2 by 2 matrix. This is a 2 by 2 matrix. So Ku belongs to M22. That means M22 is closed under scalar multiplication. That's axiom 6. Axiom 7, we try to show that K times U plus V is the same as Ku plus Kv. Here we do the addition first, do the parentheses first, do matrix addition first. U plus V is U11 plus V11, U12 plus V12. u21 plus v21, u22 plus v22. When we have a scalar times a matrix, we multiply the scalar to each entries in the matrix. Here we have k times u11 plus v11, k times u12 plus v12, k times u21 plus v21, k times u22 plus v22. Since k, u, and v's, they are all real numbers, I can distribute the real numbers. I get ku11 plus kv11, ku12 plus kv12, ku21 plus kv21, ku22 plus kv22. Then I can separate u and v right in two matrices. ku11, ku12, ku21, ku22 plus k plus kv11, kv12, kv21, kv22. On each matrix, I can pull out k. In the first matrix, if I pull out k, I get u11, u12, u21, u22. In the second matrix, if I pull out k, I get v11, v12, v21, v22. That's ku plus kv. So SCN 7 is satisfied. Next, SCN 8. We try to show that k plus m times u equal to ku plus mu. Here we treat k plus m as one scalar. Here we treat k plus m as one scalar. When we have a scalar times a matrix, we have km times u11, u12, u21, and u22. When we have a scalar times a matrix, we distribute the scalar to each entries in the matrix. Here we get k plus m times u11, k plus m times u12, k plus m times u21, k plus m times u22. Then here, k, m, u, they are all real numbers, so I can distribute. If I distribute, I get ku11 plus mu11, ku12 plus mu12, ku21 plus mu21, ku22 plus mu22. Then separate k and m, write it as two matrices. I get k11, ku11, ku12, ku21, ku22 plus mu11, mu12, mu21, mu22. Then in the first matrix, I can pull out k. If I pull out k, I get k times u11, u12, u21, u22. In the second matrix, I can pull out m. If I pull out m, I get u11, u12, u21, u22. That's the same as ku plus mu. So SCN 8 is satisfied. Next, let's verify SCN 9. For SCN 9, we try to show that k times mu is the same as km times u. Here, let's do the parentheses first. M times u. For m times u, we distribute m to every entries in u. We get mu11, mu12, mu21, and mu22. That's a matrix. That's a scalar. When we have a scalar times a matrix, we distribute the scalar to every entries in the matrix. Here I get K times mu11, K times mu12, K times mu21, K times mu22. Then here, KMU, they are all real numbers. I can group KM together. I get KMU11, KMU12, KMU21, KMU22. Then here I can pull out KM. If I pull out KM, I have U11, U12, U21, U22. That's vector U. So I get Km times vector U. So axiom 9 is satisfied. Next, let's verify axiom 10. Axiom 10 says 1 times U equal to U. 1 times U. U is U11, U12, U21, U22. When we take 1 times a matrix, a scalar times a matrix, we distribute scalar to every entries in the matrix. I get 1U11, 1U12, 1U21, 1U22. That's the same as U11, U12, U21, U22. That's the same as vector U. So 1U equal to U. Axiom 10 is satisfied. If all 10 axioms are satisfied, then we can say M22 is a vector space under the standard matrix operation. So M22 is a vector space. Under the standard matrix operation. Next example, P2 is the set of all polynomials whose degree is less or equal to 2. Show that P2 is a vector space under the standard function operations. Standard function operations means function f plus g of x equal to f of x plus g of x. Kf of x is the same as k times f of x. Those are called standard function operations. In order to show P2 is a vector space, we must verify all 10 axioms. If all 10 axioms are satisfied, then P2 under these operations is a vector space. If one of the axioms is not satisfied, then P2 is not a vector space. Let's prove it. First of all, let U equal to f of x equal to A0 plus A1x plus A2x squared. V equal to function g. Let V be B0 plus B1x plus B2x squared. Let W be function h. The h of 0 be C0, h of x be C0 plus C1x plus C2x squared. Let UVW belong to P2. Let UVW belong to P2. And let Km be scalars. First axiom, we try to show that U plus V belongs to P2. U plus V is the same as function f plus function g. function f is a0 plus a1x plus a2s squared. Function g is b0 plus b1x plus b2s squared. If we combine like terms, we have a0 plus b0 plus a1 plus b1x plus a2 plus b2s squared. That's a second degree polynomial. So that belongs to P2. That's a second degree polynomial. So that belongs to P2. That means P2 is closed under vector addition. So epsilon 1 is satisfied. What about epsilon 2? For epsilon 2, we have to show that u plus v is the same as v plus u. U plus v is function f plus function g. That's a0 plus a1x plus a2s squared plus b0 plus b1x plus b2s squared. Then combine like terms, we get a0 plus b0 plus a1 plus b1x plus a2 plus b2s squared. How about v plus u? V plus u is function g of x plus function f of x. That's b0 plus b1x plus b2s squared plus a0 plus a1x plus a2s squared. Then combine like terms, we get b0 plus a0 plus b1 plus a1 times x plus b2 plus a2 times s squared. Since the a's and b's are constants, are real numbers, then we can see that here, the coefficient of these two polynomials, they are exactly the same. So u plus v equal to v plus u. Epsilon 2 is satisfied. So here, u plus v is the same as v plus u. That means epsilon 2 is satisfied. Next, epsilon 3. For associativity, try to show that u plus v plus w is the same as u plus v, then plus w. Vector u is f of x. Vector v is g of x. Vector w is h of x. Here, function f is a0 plus a1x plus a2s squared. Function g is b0 plus b1x plus b2s squared. Function h is c0 plus c1x plus c2s squared. Then you can add the properties first. I get a0 plus a1x plus a2s squared. Inside the parentheses, if I combine like terms, I get b0 plus c0 plus b1 plus c1 times x plus b2 plus c2 times s squared. Then, when we combine like terms, I get a0 plus b0 plus c0 plus a1 plus b1 plus c1 times x plus a2 plus b2 plus c2 times s squared, which can be rewritten as a0 plus b0 plus c0 plus a1 plus b1 plus c1 times x plus a2 plus b2 plus c2 times s squared. Then on the right side, for u plus v plus w, that's function f of x plus g of x plus h of x. We'll try to show that they are the same. Function f is a0 plus a1x plus a2s squared. Function g is b0 plus b1x plus b2s squared. Function h is c0 plus c1x plus c2s squared. So let's do the bracket first. Inside the bracket, if I combine like terms, I get a0 plus b0 plus a1 plus b1 times x plus a2 plus b2 times s squared plus c0 plus c1x plus c2s squared. If I keep combining like terms, I get a0 plus b0 plus c0 a1 plus b1 plus c1 times x plus a2 plus b2 plus c2 times s squared. Then the bracket can be, those are real numbers. Inside the bracket, those are real numbers. It can be rewrite as a0 plus b0 plus c0 a1 plus b1 plus c1 times x a2 plus b2 plus c2 times s squared. So you can see that they are exactly the same. So axiom 3 is satisfied. U plus v plus w is the same as u plus v plus w. So axiom 3 is satisfied. Next, axiom 4. We try to show that zero vector exists. We don't know what zero vector is, so let zero vector equal to p of x. Assume p of x is d1, d0 plus d1x plus d2s squared. Then we know that zero vector plus u always equal to u. Zero vector is px, u is f of x. P of x plus f of x is the same as d0 plus d1x plus d2s squared. F of x is a0 plus a1x plus a2s squared equal to f of x. F of x is a0 plus a1x plus a2s squared. Then on the left side, add the polynomials. If I combine like terms, I get d0 plus a0 plus d1 plus a1x plus d2 plus a2s squared. That equal to a0 plus a1x plus a2s squared. Then by matching the coefficient, we know that we have d0 plus a0 equal to a0. d1 plus a1 equal to a1. d2 plus a2 equal to a2. Then solve the equation from the d's. In the first equation, I can subtract a0 from both sides. I get d0 equal to 0. In the second equation, I can subtract a1 from both sides. I get d1 equal to 0. In the third equation, I can subtract a2 from both sides. I get d2 equal to 0. So vector O is p of x, which is 0 plus 0 times x plus 0 times s squared, which is 0. 0 is a constant. That's a degree. Whose degree is less than 2. So 0 belongs to R2, belongs to P2. 0 is a constant. The degree of this function is less or equal to 2. So this function belongs to P2. Next, axiom 5. We try to show that for every vector u, its additive inverse exists. We don't know what negative u is, so let negative u be q of x. We don't know what it is, so let's let q of x be e0 plus e1x plus e2x squared. I don't know what it is. So let q of x, negative u be q of x, which is e0 plus e1 of x plus e2 of x squared. We know that negative u plus u equal to 0, equal to the 0 vector. Negative u is q of x, u is f of x, equal to 0 vector. 0 vector is the constant 0. 0 vector here is the constant 0. Q of x is e0 plus e1x plus e2x squared. F of x is a0 plus a1x plus a2x squared. They're equal to 0. Then add the functions. We can combine like terms. We get e0 plus a0 plus e1 plus a1x plus e2 plus a2x squared equal to 0. If a polynomial is 0, that means all its coefficients must be 0. So e0 plus a0 equal to 0. e1 plus a1 equal to 0. e2 plus a2 equal to 0. Then solve the equation from the east. I get e0 equal to negative a0. e1 equal to negative a1. e2 equal to negative a2. So negative u equal to q of x, which is negative a0 minus a1x minus a2x squared. This is a second degree polynomial that belongs to P2. P2 is a set of all polynomials whose degree is less than or equal to 2. So negative u belongs to P2. That means axiom 5 is satisfied. Next, let's check axiom 6. Axiom 6 will try to show that Ku belongs to P2. What's Ku? U is f of x. F of x is a0 plus a1x plus a2x squared. Then distribute k. I get ka0 plus ka1x plus ka2x squared. That's a second degree polynomial. That belongs to P2. Next, axiom 7. Axiom 7 says k times u plus v equal to ku plus kv. So here, k times u plus v. U plus v is function f of x plus g of x. F of x is a0 plus a1x plus a2x squared. G of x is b0 plus b1x plus b2x squared. Then do the parentheses first. Inside the parentheses, we can combine like terms. If I combine like terms, I get a0 plus b0 plus a1 plus b1 times x plus a2 plus b2 times x squared. If I distribute k, I get ka0 plus b0 plus ka1 plus b1x plus ka2 plus b2 s squared. If I distribute k, I get ka0 plus kb0 plus ka1 plus kb1 times x plus ka2 plus kb2 times s squared. If I distribute x and s squared, I get ka0 plus kb0 plus ka1 times x plus kb1 times x plus ka2 times s squared plus kb2 times s squared. Now, if I put all the a's together, all the b's together, I get ka0 plus ka1x plus ka2x squared plus kb0 plus kb1x plus kb2x squared. Then, in the first part, I pull out k. If I pull out k, I get a0 plus a1x plus a2s squared. In the second part, I can also pull out k. If I pull out k, I get b0 plus b1x plus b2s squared. That's k times f of x plus k times g of x. F of x is u, g of x is v, so I get ku plus kv. That means axiom 7 is satisfied. Axiom 8 will show that k plus m times u equal to ku plus mu. Here, k plus m is one scalar. U is f of x. F of x is a0 plus a1x plus a2s squared. When we have a scalar times a function, we distribute the scalar to each terms. So I distribute k plus m to each term. I get k plus m times a0 plus k times m times a1 times x plus k times m times a2 times s squared. Distribute a0, a1x, a2s squared. I get ka0 plus ma0 plus ka1x plus ma1x plus ka2s squared plus ma2s squared. Then group all k's together and all m's together. I get ka0 plus ka1x plus ka2s squared plus ma0, ma1x, ma2s squared. Then in the first equation, pull out k. I get a0 plus a1x plus a2s squared. In the second equation, pull out m. I get a0 plus a1x plus a2s squared. a0 plus a1x plus a2s squared. That's f of x. a0 plus a1x plus a2x squared. That's another f of x. And we know that f of x is u. So I get ku plus mu. So axiom 8 is satisfied. Axiom 9, we try to show that k times mu is the same as km times u. Here u is function f of x. F of x is a0 plus a1x plus a2x squared. If I distribute m, I get ma0 plus ma1x plus ma2x squared. If I distribute k, I get kma0 plus kma1x plus kma2x squared. Those are real numbers, so I can group km together. Those are real numbers, so I can group km together. If I factor km out, I have a0 plus a1x plus a2x squared. That's km times function f of x. And we know that f of x is u. So axiom 9 is satisfied. Axiom 10, we shall show that 1 times u equal to u. We know that u is function f of x. F of x is a0 plus a1x plus a2x squared. If I distribute 1, I get a0 plus a1x plus a2x squared. That's f of x. F of x is the same as u. So 1u equal to u. That means axiom 10 is also satisfied. Since all 10 axioms are satisfied, that means P2 is a vector space. Under the standard function operation. Under the standard function operation. Next, let me show you some properties about vector space. First of all, let me show you the cancellation law. The cancellation law says that u, v, w be vectors in a vector space V. If u plus w equal to v plus w, then we can cancel w from both sides. We get u equal to v. This is called the cancellation law. Let's prove it. When we prove it, since V is a vector space, we can use all 10 axioms. We can use all 10 axioms in a vector space to prove this law. We can use all 10 axioms in V to prove this law here. Since V is a vector space, and W belong to V, then by axiom 5, the additive inverse exists. Since W belongs to V, by axiom 5, additive inverse of W exists. We know that U plus W equal to V plus W. I can add negative W to both sides. This is the equation. I can add negative W to both sides. Then, by associativity, by axiom 3, apply associativity. left side and right side can be rewritten as u plus w plus negative w. Right side can be rewritten as v plus w plus negative w. And then by axiom 4, u plus w plus negative w is 0. W plus negative w is 0. By axiom 5, w plus negative w is 0. W plus negative w is 0. And then by axiom 4, u plus 0 is u. V plus 0 is v. We prove that u equal to v. If u plus w equal to v plus w, then u equal to v. We can cancel w from both sides. This is called the cancellation law. Next, let me show you more properties about vector space. The V be a vector space, the U belong to V, and the K be a scalar. Then 0 times U equal to the 0 vector. K times the 0 vector is the 0 vector. Negative U is the same as negative 1 times U. The additive inverse, negative U, is the same as negative 1 times U. If Ku is 0, then either K is 0 or U is 0. Let's prove it. Let's prove it using the 10 axioms and the cancellation law. Let's prove it using the 10 axioms of V and the cancellation law. For part A, let's try to prove 0U equal to 0 vector. 0U can be rewritten as 0 plus 0 times U. 0 is a scalar. That's a real number. 0 can be rewritten as 0 plus 0 times U. Then, by axiom A, I can distribute U. These two zeros, they are scalars. By axiom A, I can distribute U. So I get KU, MU. By axiom A, I can distribute U. I get 0U plus 0U. So we know that 0U equal to 0U plus 0U. Then by axiom 4, the left side, 0U can be rewritten as 0U plus 0 equal to 0U plus 0U. Left side can be rewritten as 0U plus 0. Axiom 4 says every vector can be written as 0 plus no vector. Axiom 4 says every vector can be written as 0 plus no vector. This is 0 vector. So this is a vector. This vector can be written as 0 plus no vector. This vector can be written as 0 plus no vector. By axiom 4, leave the right side the same. Then, by cancellation law, by the cancellation law, I can cancel 0U from both sides. I cancel 1 of the 0U from both sides. I get 0 equal to 0U. I cancel 0U, 1 of 0U from both sides. I get vector 0 equal to 0 times U. That proves the first one, the first statement. 0U equal to vector 0. Part B, prove that K times 0 vector equal to 0 vector. The proof is very similar. We know that K times 0 vector can be written as 0 vector plus 0 vector. By axiom 4, every vector can be written as the vector itself plus the 0 vector. By axiom 4, every vector can be written as the vector itself plus the 0 vector. 0 vector itself is a vector. This vector can be written as the vector itself plus the 0 vector. Then by axiom 7, k is a scalar. I can distribute k into the premises. By axiom 7, we have k times the sum of two vectors. I can distribute k to both vectors. So we have two vectors in the premises. I can distribute k. I get k0 plus k0. So k0 equal to k0 plus k0. So here k0 equal to k0 plus k0. Then by axiom 4, the left side, k0 can be written as k0 plus 0. By axiom 4, the left side, k0 is a vector. This vector can be written as the vector plus 0 vector itself. Axiom 4 says any vector can be written as the vector itself plus 0. So here k0 is a vector. This vector can be written as the vector itself plus the 0 vector. Leave the right side the same. k0 plus k0. Then by the cancellation law, I can cancel k0 from both sides. Cancel k0 from both sides. I get 0 vector equal to k0. That proves the second statement. The third statement, we try to prove that the additive inverse negative u is negative 1 times u. By part A, we know that 0 times u equal to the 0 vector. And number 0 can be written as negative 1 plus 1. Number 0, this 0 is a real number. 0 can be written as negative 1 plus 1. Then, by axiom A, we can distribute vector u into the premises. Since those are two scalars, by axiom A, I can distribute u into the premises. So I get negative 1 times u plus 1 times u. And we know that 0 vector can be written as u plus negative u. 0 vector can be written as negative u plus negative u, or negative u plus u. By axiom 5, 0 vector can be written as u plus negative u, or negative u plus u. So on the left side, by axiom A, I distribute u. I get this. On the right side, by axiom 5, 0 vector can be written as negative u plus u. Then by axiom 10, we know that 1u is u. By axiom 10, we know that 1u is u. So negative 1 times u plus u equal to negative u plus u. Then by the cancellation law, I cancel u from both sides. By cancellation law, I cancel u from both sides. I get negative 1 times u equal to negative u. By cancellation law, I cancel u from both sides. I get negative 1u equal to negative u. That's statement C. Negative u equal to negative 1 times u. Statement D, try to prove that if ku is the 0 vector, then either k is 0 or u is 0. If ku is 0, then either k is 0 or u is 0. So for part D, ku is 0. This assumption. Assume k is not 0. Assume k is not 0. Then 1 over k is a real number. Assume k is not 0, then 1 over k is a real number, 1 over k exists. Ku equals 0. I can multiply both sides by 1 over k. I can multiply both sides by 1 over k. Then 1 over k times ku by adding a 9. By adding a 9, 1 over k times ku by adding a 9. When we have a scalar times a scalar times a vector, we can multiply the scalar first and then times the vector. By adding a 9, left side can be rewritten as 1 over k times u. And the right side, we have 1 over k times the 0 vector. By part B, we know that any scalar times the 0 vector is 0 vector. By part B, we know that any scalar times the 0 vector is the 0 vector. So by part B, any scalar times the 0 vector is the 0 vector. So left side is by adding a 9. 1 over k times ku, I can multiply a scalar together, then times the vector. On the right side, by statement part B, by the property part B, any scalar times the 0 vector is the 0 vector. We got this statement here. Next, we know that 1 over k times k, that's 1. For any real numbers, 1 over k times k is 1. So I get 1 times u equal to the 0 vector. And then by adding 10, 1 times u is u. So here we see that if k is not 0, u must be 0. That means either k is 0 or u is 0. If k is not 0, then u must be 0. That means either k is 0 or u is 0. That completes the proof.